Okay, so today we're talking about graphing exponential functions. Exponential functions do not have one specific parent function, but rather they have different parent functions depending on the base. So the form for your parent function is f of x equals b to the x power. Which of those b or x is your base? B. It's the value that is being raised to a power. And what's the exponent? X. That's how we know that this is an exponential function, because the variable is in your exponent. Okay? Variable is in your exponent. All right, so a couple things about this like non-parent function, if you will. B is what kind of determines your parent function, depending on your base. Your base can be a couple different things, but it does have some restrictions. Okay? B has to be greater than 0. Let's talk about why. Think in your head for a moment if B was negative 2. Okay? If B was negative 2, what's negative 2 to the first power? Negative 2. What's negative 2 squared?
4.
Positive 4. What's negative 2 cubed?
Negative 8.
Negative 8. What's negative 2 to the fourth?
16.
Positive 16. So do you see how it would keep going up, and down, positive, negative? So we couldn't get a smooth exponential curve, which is why your B value could never be negative. Okay? Your B value can also never be 1. Why not? Yeah, it would just be 1, right? 1 raised to any power is just 1. So that would just be the line f of x equals 1. Yeah.
If you tried to plug into a graph of b being negative or 1, it wouldn't, would it show, is it actually a graph?
I mean, it's a graph. It's just not an exponential function.
Okay.
For this to be an exponential function, b has to fit these requirements.
So can b be like 1 half?
Yeah. Any positive number except 1. All right, look at number 1. F of x equals 2 to the x. This is one of our parent functions. Okay? This is a parent function. What is the base? 2. What's the power? How do I know this is exponential?
Because the variable is a power.
Good, because the variable is in the exponent. All right, so we're going to go ahead and fill out this table from negative 3 to 3.
Are there any restrictions on that?
No, you're going to see that in a minute when we look at the domain. Okay, let's start with the positive powers because those are a little easier. What's 2 to the first? 2 squared. 2 cubed. Okay, what's 2 to the 0 power?
1.
1. All right, let's think about it. What's 2 to the negative 1 power?
1/2.
What is that? 1/2. Remember that a negative exponent, you flip your base, right? And then you have a positive exponent. All right, what about to the negative 2 power? 1/4. And then to the negative 3. All right, let's plot this.
So if you have a positive base, that means that your f of x value will never be negative?
Let's look at the graph real quick. All right, so what's going to keep happening as your x value decreases? Gets closer and closer to 0. Is it going to hit 0? No, we can't raise 2 to a power and get 0. So if we are going to get closer and closer and closer to 0 but not hit it, what do we call y equals 0? Asymptote. All of your exponential parent functions will have a horizontal asymptote at y equals 0. So then you can draw in your exponential curve. All right, and I want to draw your attention to this point right here, 0, 1. Is that point dependent on our base?
No.
No. No matter what base we put in there, if we raise it to a 0 power, it's going to be 1. So this point is always a part of your parent functions, no matter the base. You're always going to have that point, and you're always going to have the horizontal asymptote at y equals 0. This function is increasing or decreasing? Increasing. How do you know?
Will it always be increasing?
We're going to see some examples and make a generalization in just a minute of when it's increasing or decreasing. So as our x values increase, our f of x values are also increasing. What we call that is exponential growth. Okay, what's the domain of this function? And what's the range of this function? Okay? All right. Will you please fill out your table in graph number 2? Make sure to label your asymptote and your domain and range. -3 to 3. You're not going to be able to plot all of them, but you can go ahead and fill them out. All right, take a look up here and make sure your graph looks like this. Are there any questions on graphing f of x equals 3 to the x power? This is another parent function. This is a parent function for anything that has a base of 3. Everyone okay? All right, let's look at number 3. What's different in number 3 than our other functions? Okay, the base is a fraction. So that's going to cause a change that we're going to find out in just a minute. So let's just go ahead and fill out our table. I know that 1/2 to the 0 power is going to be 1. 1/2 to the first half power is 1/2. What's 1/2 squared? And 1/2 cubed? Okay. What is 1/2 to the -1 power? 2. Everyone okay with that? We flip it and then raise it to the first power. What's 1/2 to the -2 power? And to the -3? All right, so go ahead and plot that. Okay, do we still have an asymptote? Where? This time, is our graph increasing or decreasing? Decreasing. So we call this exponential decay. What's the domain? And what's the range? Okay, on this one, like on some of your homework, it is not necessary to fill out the entire table. You can kind of just get an idea for what's happening, okay? So, first of all, to help me visualize this, I'm going to rewrite this as 4/5 to the x power, because that's easier for me. If I plug in 0, I know I'm going to get 1, right? That's always on my parent functions. What if I plug in positive 1? Just going to get 4/5. What if I plug in negative 1? Good, it's going to flip it, right? 5/4. So think about your graph. What's happening to it? It's decreasing. So is this exponential growth or decay? You don't have to fill in the tables that they give you. You don't have to fill in all of the tables they give you. You can just fill in a couple points to help you get an idea. If you wanted to calculate a few more points, that would be totally fine. Okay? For the parent functions, yes, your domain and range will always be the same. But once we start doing transformations, the range can change. What is our domain? Okay? All right, let's sum this up a little bit. Compare your 4 graphs that we've graphed at this point. When is our graph increasing and when is our graph decreasing?
When the base is greater than or equal to, or greater than 1.
Okay, so when our base is greater than 1, why not equal to? Good, can't be equal to 1. When the base is greater than 1, our graph is increasing, which means exponential growth. The reason this is important is it kind of gives us an idea of what the graph looks like. If you can decide before you start graphing exponential growth versus exponential decay, you know what this general shape is going to look like. Okay, what are the restrictions on B for it to be decay? Between 0 and 1. All right, everyone okay with that? All right, let's talk about some transformations. All right, so I could have the equation y equals a times b to the x minus h power plus k. All right, these are functions. These follow our same function transformation rules that we've been doing all year. So what does the a do? vertical stretch or compression. When A is greater than 1, we have a vertical stretch. When A is between 0 and 1, we have a vertical compression. What happens if A is negative? Go to reflection how? Good. A is negative, you reflect across the x-axis. Okay? What does the H do?
Move it over.
Let's be a little bit more technical than that. Okay, so horizontal translations. Okay, and what about K? Okay, these are the ones that we're really concerned with. These are the ones we're going to do the majority of the time. But I do want to remind you about that pesky little horizontal stretch and compression. Okay, we don't do it that often, but you do need to remember it. So if I gave you the equation y equals 3 to the 2 times x minus 1 power. Remind me what that 2 does.
No,
It's a horizontal stretch or compression? Compression, good, because it always does the opposite, right? So it's a horizontal compression. So you need to be able to take that from an equation and write it out for me, that it's a horizontal compression. Or if you're told, write an equation with a horizontal compression, you need to know where it goes. But we're not really going to worry about graphing it, so just worry about knowing and recognizing it, okay? All right, let's graph a little bit. F of x equals 3 to the x minus 3 power plus 1. What is the parent function here?
3x. 3 to the power of x.
3 to the power of x. Is that growth or decay? How'd you know?
because
Greater than 1.
What's it?
Oh, B value.
Good. The b value is greater than 1. All right. What are the transformations that have happened? Right? 3.
1.
Up 1. Okay. Think about those two things I told you were on every function, every parent function. We have a horizontal asymptote, we have the point 0,1. I want you to think about that horizontal asymptote. What type of transformations affect a horizontal asymptote? Vertical shifts up or down. So that shift up is going to move our horizontal asymptote from y equals 0 to y equals 1. Your asymptote is always the first thing you want to plot. Okay with that? All right, now take your point 0, 1 and transform it. Right 3, up 1. We know this is growth, so we're going to follow the path of exponential growth. And we're going to sketch our graph.
So 1 point is all you need.
For right now, we're just focusing on the shape, yes. Okay, what's the domain? And what's the range? For right now, we're just sketching the shape of the graph. So the only point you really need to worry about is 0, 1. If you want to plug in more points, you definitely can. Okay, let's look at number 6. What is the parent function? It's not 1/2 x, guys. 1/2 to the power of x, or to the x power. All right, is that growth or decay? Decay. Helps me to kind of trace the shape of growth and decay so that I know what I'm about to graph. Okay? All right, let's talk about the transformations. What are the transformations? Reflect across x, then down 2. So what's the first thing I should plot? My asymptote. And where is my asymptote going to be?
-2.
Y equals -2. All right, take your point 0, 1. And plot that transformation. So we reflect across x and go down 2. Now with these reflections, sometimes it might help you to kind of get an idea of the shape of the graph, right? So we know our original graph looked something like that. Would you agree?
Yep.
So when you reflect it, you need to be envisioning that shape so that you know how to reflect it. What is our domain? And what's our range? Good. All right, I want you to try number 7 and 8 on your own. Well, you can definitely talk to someone next to you about them, but I want you to try 7 and 8. Talk it out with each other. Pay attention to your asymptotes and your point 0, 1. Pay attention to the asymptotes and your point 0, 1. That's why you're talking about it. Yeah, but you lose a point on that. All right, let's talk about what happened on number 7. Did your asymptote move? Your horizontal asymptote? No, it's still at y equals 0. So that means we couldn't have had a vertical translation. Okay? Your point 0, 1 moved to 4, 1. So what does that mean? Right 4. So how do I represent that? You all just lost a point. Thank you. F of x equals, or y equals 2 to the power of x minus 4. Everyone okay with that?
Yes.
All right, let's talk about number 8. Where is the asymptote on number 8? Y equals 0. So could you have translated this function up? No. So I know when I first looked to go from 1 to 3, I thought I would just add 2. But if I added 2, where would my asymptote go? Up 2 as well. So instead, what's another way you can stretch something from 0, 1 to 0, 3? A vertical stretch by what? By 3. Because you take the point 0, 1, you multiply your y value of 1 by 3, and that gives you 0, 3. So your equation should be f of x equals 3 times 2 to the x power. I'm sorry?
Why couldn't it have moved left 3
Because I wouldn't try and go left or right on this case because you don't know for certain that that point is at negative 1.5 comma 1. I would go with with points you're certain about. Okay? All right, look at number 9. Let's describe these transformations. Vertical compression by what? Okay. Then what? Left 1. Then what? 1, 3. All right. Quick refresher course on telling what type of function we've got from a table of data. Okay? If we have a linear function, then when we check our data, remember that you're going to have a constant first difference. Okay, that means when you subtract all the difference between the y values are all going to be the same. How do you know if you have a quadratic? Good. Constant second difference. Okay, an exponential function does not use differences, but rather for an exponential function, you're going to have a constant ratio. Which makes sense, because if we're raising a number to a power, each time we plug in a new x value, we multiply by that number. So to check for a constant ratio, you see if you can just see if you're multiplying by the same thing each time, or you divide each number by the previous y value and see if it's constant. So look at number 10. What do you think? Linear, quadratic, exponential, none. Exponential, how'd you know? Constant ratio of 4. You're multiplying by 4 each time. If, like you have on your homework, if you have decimals here and you're not sure, just divide the number by its previous number and see if it's constant. Okay? So this constant ratio, that's our b value. And this 0, 1, that y-intercept of 1, that is our a value. So the equation of this exponential function is y equals 1 times 4 to the x power. That 1 is not necessary. I'm just putting it there in case you forget that that's where it would go. Okay, what about number 11? It's linear. How do you know? Yeah, constant first difference. Plus 1, plus 1, plus 1, plus 1. Okay? A note about your homework. The tables that are next to the ones for you to graph, you do not have to fill those out completely. Just get 3 or 4 points so that you know what the shape of the graph needs to look like. Okay?